Now let's take a look at the architecture of Kubernetes. So Kubernetes consists of a lot of components, mainly Kube API server, Kube scheduler, Kube controller manager, etcd, Kubelet, and Kube proxy. So it is distributed across the master node or the control plane and the worker nodes. So the master node contains Kube API server, Kube controller manager, Kube scheduler, and etcd. We will look into each of these components in detail. And on worker nodes, we have Kubelet and Kube proxy. So it is in the worker nodes where the workloads are running on pods. And each of these pods runs containers. So all of these together creates the cluster. The first component is Kube API server. So the Kube API server is a very key component of the Kubernetes architecture. It is the central control plane component that exposes the Kubernetes API and processes all RESTful API requests sent to the Kubernetes cluster. The Kubernetes API server will be responsible for serving the Kubernetes API. Kubernetes API, it provides a programmatic interface for managing this cluster. The API is used by various Kubernetes components and external tools to interact within the cluster. Kube API server is also responsible for authenticating and authorizing API requests. So it authenticates and authorizes all the API requests that are sent to the cluster. It uses the Kubernetes authentication and authorization plugins to verify the credentials of the user or application making the request and to ensure that the request is authorized based on the user's role or permission. And it is also responsible for validating and admitting API requests. The Kube API server validates and admits all API requests that are sent to the cluster. It checks that the request is properly formatted and contains all the information. It also runs admission control plugins, which can modify or reject requests based on custom rules and policies. And it is also responsible for managing the state of the cluster, including all configuration of Kubernetes objects such as pods, services, etc. And it stores the state in etcd, which is a distributed key value store that provides a reliable and consistent data store for the cluster. So the Kube API server is designed to be highly available and fault tolerant. It can be run in a clustered configuration with multiple replicas. And it supports various authentication and authorization mechanisms, including client certificates, bearer tokens, and OpenID Connect. So in summary, the Kube API server is a critical component of the Kubernetes architecture. And it provides a central point of control for managing the cluster and ensuring that all API requests are authenticated, authorized, and validated. So it is really important to understand how the Kube API server works for anybody who is looking to deploy and manage Kubernetes clusters. And the next component is Kube scheduler. Kube scheduler is a key component of Kubernetes, and it is responsible for scheduling pods and deployments into nodes in the cluster. It runs as a single process on the master node of the cluster and is responsible for ensuring that the pods are scheduled to run on the most suitable node based on their resource requirements and other constraints. The Kube scheduler is responsible for node selection, resource allocation, interpod affinity, node constraints, etc. The Kube scheduler selects the most appropriate node to run a pod based on the pod's resource requirements and other constraints such as node affinity or anti-affinity. The kube scheduler ensures that the resources required by a pod, such as CPU and memory, are available on the selected node before scheduling the pod to run. And the kube scheduler also takes into account the affinity and anti-affinity requirements of pods when scheduling them onto the nodes. This ensures that pods that need to be co-located are scheduled on the same node. The kube scheduler also takes into account the constraints on the nodes, such as stains and tolerations, while selecting the nodes to schedule the pods. We will look at stains and tolerations and affinity in a later course, but let's stick to the basics for now. The kube scheduler uses a scheduling algorithm to determine the best node to schedule a pod based on the resource requirements and the constraints of a pod. The scheduling algorithm takes into account a number of factors, including CPU, memory usage of the nodes in the cluster, the storage, and the network resources available, and the affinity and anti-affinity requirements of the pods. Once the kube scheduler has selected a node for the pod, it communicates with the kubelet on that node to schedule that pod to run. The kubelet then downloads the container image for the pod and starts the pod's container. So in summary, the kube scheduler is a critical component responsible for scheduling pods into nodes in the cluster. The next component is Kube Controller Manager. Kube Controller Manager is a key component responsible for managing the controllers that regulate the state of the cluster. It again runs as a single process in the master node. It is responsible for ensuring that the desired state of the cluster is maintained. So the Kube Controller Manager has a few controllers within, such as node controller, replica set controller, deployment controller, and stateful set controller. It also has service controller. The node controller is responsible for monitoring the nodes in the cluster and ensuring that the desired state of the nodes is maintained. And this also includes detecting when nodes become unhealthy or unavailable and taking actions to address these issues. Replica set controller is responsible for ensuring that the correct number of replicas of a particular pod is running in the cluster. It monitors the desired state of the replica set and takes action to create or destroy pods as needed to ensure that the desired state is maintained. Deployment controller is responsible for managing the lifecycle of a deployment. It monitors the desired state of the deployment and takes action to create or destroy replica sets and pods as needed to ensure that the desired state is maintained. Stateful set controller is responsible for managing the lifecycle of stateful applications in the cluster. It ensures that the correct number of replicas of a particular stateful application is running in the cluster, and it also takes actions accordingly. Service controller is responsible for ensuring that the correct endpoints are available for services running in the cluster. It monitors the state of the service objects and takes action to update it accordingly. So, Kube Controller Manager is responsible for managing the replicas, endpoint, service accounts, and other resources as well. And it mainly ensures the desired state matches the actual state. And you can also extend it for custom controllers. And it is also a very critical component for automation management and ensuring the cluster health. So the Kube Controller Manager works closely with other Kubernetes components such as Kubelet and Kube proxy to ensure that the desired state of the cluster is maintained. It communicates with the Kubernetes API server, which is Kube API server. to receive instructions about how to manage the controllers in cluster and reports the status of the controller back to the API server. The next component is etcd. etcd is a distributed key value store that is a critical component of the Kubernetes architecture. It is used by Kubernetes to store and retrieve configuration data and state information. etcd is responsible for maintaining the state of the entire Kubernetes cluster, including information about nodes, pods, services, and other Kubernetes resources. etcd is designed to be highly available and fault tolerant. It uses a distributed consensus algorithm to ensure that the data is replicated across all the nodes in the cluster. And it can survive network partitions and node failures. etcd also supports automatic leader election and automatic data compaction, which helps to ensure that the cluster remains healthy and efficient. Some of the features of etcd includes distributed consensus, which means that it uses a distributed consensus algorithm to ensure that the data is replicated across all the nodes in the cluster. And each node has a consistent view of the cluster's state. And etcd is also designed to be highly available with built-in support for automatic leader election and node failover. etcd is also designed in such a way that if one etcd fails, the other candidates will elect the next leader. And etcd also provides a simple API interface that can be used to store and retrieve configuration data and state information. It also supports a watch API that can be used to monitor changes to the key value store in real time. And it also supports role-based access control, also known as RBAC, and TLS encryption to secure access to the key value store. It is also highly scalable with support for tens of thousands of writes per second. And it is very critical for managing the stateful workloads, also the entire cluster, and ensuring the system's health. The next key component is Kubelet. Kubelet is responsible for managing the state of individual nodes in the cluster. It is responsible for starting and stopping containers in a node, and it monitors the Kube API server for changes to desired state of the containers and ensures that the containers are running as expected. It also regularly checks the health of the containers it manages and reports the status of the containers to the Kube API server. If a container is found to be unhealthy, a kubelet can automatically restart or replace the containers. It is also responsible for managing the resources used by the containers on a node, such as CPU, memory, and storage. And it enforces resource constraints specified in the pod manifest and ensures that containers do not exceed their allocated resources. It is also responsible for managing volumes attached to the containers. It mounts volumes specified in the pod manifest and ensures that they are available to the containers. Kubelet also reports the status of the node to the Kubernetes API server. This includes information about the node's available resources, the status of the containers running inside the node, and any events or issues affecting the node. The kubelet runs on each node in the cluster and communicates with the Kube API server to receive instructions about how to manage containers on the node. It works closely with other components such as the Kube proxy and Kube controller manager to ensure that the containers are running as expected and the cluster is operating smoothly. And the next component is Kube proxy. Kube proxy acts as a network proxy or a load balancer for services running on a Kubernetes cluster. It is responsible for routing traffic to the appropriate pod and container based on the rules defined in the Kubernetes service object. So the Kube proxy is responsible for service discovery, load balancing, health checking, and network proxying. So the Kube proxy discovers the services running on the Kubernetes cluster and maps them to the IP address of the pods and containers that make up the service. And the Kube proxy also load balances the traffic across the pods and containers that make up a service, and it distributes the load evenly, ensuring that each pod receives a fair share of the traffic. And it also regularly health checks the pods and containers that make up a service and remove any that are found to be unhealthy. It also acts as a networking proxy for services running on the cluster, forwarding traffic to the appropriate pod and a container based on the rules defined on Kube service. The Kube proxy can be run in two different modes. One is user space mode, where Kube proxy run as a user space process on each node in the cluster. And it will be responsible for forwarding the traffic to the appropriate pod and container using NAT or Network Address Translator. And the second mode is IP tables mode. And in this mode, Kube proxy uses IP tables firewall to forward traffic to the appropriate pod and container. This mode is more efficient than user space mode and is the default mode used by most of the Kubernetes clusters. And it also implements network policies to restrict traffic between pods and services, and is also very essential for ensuring reliable communication between the application. In the upcoming lecture, we will discuss about how we can set up a Kubernetes cluster.